reactions, but I only had 2 of the 3 driving forces. We talked about precipitation reactions, molecular, ionic, and net ionic equations, and we used our solubility table to find the driving force, that insoluble product. We talked about acid-base neutralization, where an acid starts with an H and a base ends with an OH, and the driving force is making molecular water. I asked you to memorize or have handy somewhere on a test-taking tool page the 7 strong acids so that you memorized all of the weak ones as well. And we practiced by making sure we only dissociated the strong acids as we worked to the net ionic equations. You see the work left in this section is significant. I need to talk about one more pattern of chemical change, a gas-forming reaction, and then switch gears to talk about electron transfer in what we refer to as oxidation and reduction reactions. This will be the focus of today's lesson, making us push the math forward until next week, Tuesday. Tuesday night, your sapling is due. Wednesday night, your multiple choice test is due. All right, just kind of pushing the timelines ahead. Let's begin with the next step of a double replacement, talking about a third type of driving force. First type, precipitate. Second type, acid-base. The third evidence of chemical change is seeing a gas formation. When I put 2 aqueous solutions together, does it make some bubbles? If it bubbled, that's evidence of a chemical change. Very specific to this type of pattern, of all of those that I could make you ask you to learn, I'm asking us to recognize the carbonate polyatomic ion. When I see carbonate, I'm going to suspect some bubbling. Just like a carbonated beverage, if you open a can of pop, it will bubble, releasing carbon dioxide bubbles. That's the pattern. It's just the one little thing we're going to ask you to know about the driving force of a gas formation. In a double replacement reaction, let's find sodium hydrogen carbonate as our first reactant. That's fancy for saying baking soda. Sodium hydrogen carbonate. I know sodium has an elemental symbol Na. The periodic table allows me to find its charge. When it forms an ion, it's in that first column, so we know it's a +1. On your polyatomic page, you see a polyatomic ion in the very first column, and it's called hydrogen carbonate. And if you're using the one that I had from Canvas and you printed that, you'll see my handwriting underneath it, and it says, sometimes we call that bicarbonate. Hydrogen carbonate or bicarbonate has a formula of HCO3 -1. So sodium's +1 is electrically balanced with bicarbonate's -1. Sodium hydrogen carbonate, baking soda. It's in an aqueous solution, as all of the double replacement patterns must be in an aqueous solution so that these ions have a way of exchanging. It's reacting with acetic acid, commonly called vinegar, acetic acid. You're titrating with that this week in the lab. It stinks in there, doesn't it? Like an Easter egg hunt. It's vinegar smell. Hydrogen acetate. Hydrogen is a +1. Acetate is a polyatomic ion with a -1 charge. Acetic, this ic, came from 8. So to write that formula, I had to look up acetate. H+ makes it an acid, the acetate ion, and it comes out electrically balanced. Keep in mind the 4 characters. We have compound A, B, reacting with compound C, D. Oops, I missed. Sorry, there's a 2 with that oxygen. I missed that. C2H3O2 is the acetate. Now remember, double replacement, I don't care if it's precipitation, if it's acid-base chemistry, or with our new driving force, we take those two positives and we just change their partner. So where the sodium is now, we'll get a new last name. It will be called acetate, sodium acetate. The hydrogen will go to hydrogen carbonate. So one of my products, the salt of sodium acetate, Na is a plus, acetate's a minus, so we find NaC2H3O2, sodium acetate. Acetates are always soluble. If you were to use your solubility table and found the element sodium, the very bottom one on the left chart is acetate. It has a green soluble note. Acetates are always soluble, so AQ for its adjective. And when H hooks to HCO3, I'll combine those to make H2CO3, and that is called carbonic acid. When you form carbonic acid, H2CO3, it is so unstable, it immediately decomposes. It breaks down. A decomposition reaction to break into simpler pieces. When it decomposes, I'll just write that here. When H2CO3 breaks into simpler pieces, it bubbles. It's the evidence of change that you see when baking soda and vinegar come into contact with one another. You see it start bubbling. The identity of those bubbles is carbon dioxide gas. And if you remove a CO2 from H2CO3, what's left? And water. Carbon dioxide comes bubbling out as a gas, and liquid water remains. So when we see carbon dioxide generated, we do a double displacement first and then decompose the acid so that at the end, there's actually three products to our balanced equation. Because the carbonic acid decomposed into carbon dioxide gas and water, and still in that water would be the sodium acetate. There's three products at the end. A chemical change, right? It's just evidence that we made something new if something starts to bubble. Just like precipitation, if I see solid chunkies form, that's evidence of change. With your acid-base neutralization, you will see today in lab, or you have seen earlier, evidence of neutralization. When you reach the end point, you see a color change from that indicator called phenolphthalein. Ready? So there's evidence of change. When I write out NaHCO3 aqueous with acetic acid, which we called vinegar, aqueous, we saw a salt form, sodium acetate aqueous, and we saw carbon dioxide gas and liquid water. This is what we refer to as the molecular equation. I just rewrote the exact same thing, but instead of a stepwise decomposition, I'm showing these are the reactants and the three final products. The driving force is the production of the carbon dioxide gas. You're seeing bubbles that weren't there before when this salt reacted with vinegar. What would the net ionic equation look like for this particular reaction? Now remember, we're only allowed to break apart strong electrolytes, and we've been working hard at recognizing strong electrolytes. Any soluble salt is a strong electrolyte. Sodium acetate is a strong electrolyte. It's water soluble. Acetic acid, vinegar, is that one of our 7 strong acids that we're working to memorize. I see you're shaking your head. Nope, that's not on the list. So that's weak, by a weak electrolyte. On the product side, sodium acetate. That's a water-soluble salt. It's aqueous. It's a strong electrolyte. Carbon dioxide and water. Both of these are molecular compounds. Molecular compounds are not built of ions. They are classified as non-electrolytes. That's the critical step in deciding what do I break apart and what do I leave together to turn my molecular equation into the net ionic equation. When sodium hydrogen carbonate breaks apart, we see an aqueous ion of sodium and an aqueous ion of bicarbonate. Acetic acid, you told me, was not one of the 7 strong, so therefore we know we must leave it together. Sodium acetate is a strong electrolyte, therefore it dissociates into its ions of sodium and of acetate. We broke apart the soluble salts. We leave together the weak acid and the molecular compounds, carbon dioxide and water. This is called the ionic or complete ionic equation. I broke apart the molecular strong electrolytes and asked you which one of those, if any, do you see are called spectator ions. Which ions are only there to neutralize charge but did not partake in a chemical change? I see sodium. And that's it. The spectator ion is simply the sodium ion. Now, if I eliminate that, you would write the net ionic equation is everything the same, but with no sodium. You'd have an aqueous ion of bicarbonate reacting with the weak acid, acetic acid, forming the acetate polyatomic ion, the bubbles of carbon dioxide, and the water as a liquid form. Keep in mind the acetate, sodium acetate, would be in the water, carbon dioxide bubbled out of your dish. You did this very experiment, or a similar one, a few weeks back in lab. You poured acid onto this white solid and it bubbled, and your job was to get it to not bubble anymore and then heat it, dry it, and weigh it. That evidence of change was making a gas. Even though this is presented as a third type of equation, it's nothing more than what we've been practicing, a double replacement, except now we have a different type of observation. We see bubbles. We could have seen a solid precipitate, or we could have had an acid neutralize a base. This question that we just worked through is one of your homework questions on sapling. You now have an answer to this question when you see it on sapling. It says you take some baking soda, NaHCO3, and vinegar, which is primarily acetic acid. And this is a little video that plays when you open up this question. It will be fizzing or bubbling. And it says, what's going on there? It asks us to finish that equation out, including the phases. Complete the following equation for this reaction. You now have that to bring home and finish that homework question. What it's asking is this equation. When sodium acetate reacts with acetic acid, sodium acetate, carbon dioxide, and water will form. Including the phases, you type that into the blue box. Now notice that it doesn't ask me for the net. It just asks me for the equation with the phase symbols. So I don't have to do that next step for this particular question. I'll put it back. On your paper to turn in today, let's try another. Let's find potassium carbonate and react it with hydrochloric acid. Notice the word carbonate. When you see carbonate, suspect bubbling. Alrighty. Potassium carbonate with hydrochloric acid. Complete the molecular and turn it into a net ionic equation. Do you need a periodic table, polyatomic? Do you have any of those tool pages with you? That would help. Yeah. Bless you.
Because hydrochloric acid is a single unit, would it be a single or?
Nope, it's made of two different ions, H plus and Cl negative. Don't forget this guy's a plus and that's a minus 2. It breaks apart into 2 K plus and 1 CO3 minus 2. Right now, you haven't balanced yet, but your skeleton, almost. Like you have to do some charges, like even with that guy. Excellent. One thing is just to balance that, and you got it. Good work. Good, good, good. Really good start. Good work. You're off to a really good start. Really good. Yep. Sometimes just having a little boost of confidence, like good work, right? Well, one thing is, and everything you're doing here is perfect. You've got charges written on top of here. We just now have to crisscross to write the compound. So if K is a plus and carbonate's a minus 2, how do we create a neutralized formula? Like when you crisscross, what would the subscripts become?
Oh, okay.
Perfect. Yes. And then this guy's good. This guy is good because it's plus 1. Oh, nope. I'm glad you said that, though, because it's so tempting that because I wrote a 2 here, you just bring it over. But remember, K, he's still a plus 1. Chloride's still a minus 1. K plus, Cl minus, we're good. But H, it's still a +1. Carbonate's still a -2. Now what? Aha. Now balance, and you're there. See how close you were? Mm-hmm. So carbonate is a -2 charge, which is, I believe, why you put a 2 there. +1 -2, you need a 2 there. And that's why it will mix. 100% of the time, if it's not balancing, it's a little subscript somewhere that went wrong. Mm-hmm. I'm seeing a ton of good work out there. That's about how far I see people so far, is about where I see most of us at, where I've come up with a molecular equation. I like seeing the charges on top. That's a really good pattern. It helps me write the formulas correctly on the product side. Perfect. Is that the hand? Perfect. Because I walked away and started talking as I got excited. Yeah. So 2, there. Now we're balanced. We're good there. Why'd I put arrows kind of pointing out of the carbonic acid? Beautiful. That as soon as that forms, it breaks apart to show me the driving force of water and carbon dioxide. So I write that as my initial product, but it doesn't stay there long, does it? As soon as it forms, we see evidence of bubbles break it down into water and carbon dioxide. I'm going to stay quiet a little longer to give you an opportunity to work ahead of me and go to the next step. Show me how to write that net ionic equation. Decide what's strong and break it apart. Oh. Oh, I would just write that as 2H+. Mhm. Mhm. Perfect. Uh-huh. Yes. Yes. It's both. It's gone. That's perfect. You got it. Yay. Whee. Potassium carbonate is a strong soluble salt. Break it apart. HCl, hey, that's one of our 7 strong acids. Break it apart. KCl, that's a strong soluble salt. Break it apart. Water, it's molecular. Carbon dioxide, molecular. Those are non-electrolytes. You leave them together. When I look at the strong electrolytes and break them apart, I can recognize the net ionic equation. I see 2 ions that would be spectators. Can you find them? What 2 ions are now spectators? Excellent. Perfect. So potassium, we broke it apart. HCl, we broke it apart. Chloride appears, potassium appears as spectators. They would be in the dissociated form. So I would have carbonate as an aqueous ion. I'd have 2 hydrogen ions because I eliminated the potassium and the chloride from the left side as spectators. And over on the product side, we'd see those coming out as liquid water and carbon dioxide gas. It's like when I walk away and think I'm balanced and I'm not, yeah. All right, 100 more reps and we'll have it, right? Good work. Yes. That's a really good question. When I share that, the question was, does the hydrogen have to be first because it's first over here? And I'll say any textbook that you see always lists the positive ion first. It's not wrong the way I have it. It's just not how you see it standardized. It would be similar to saying 3 plus 2 is 5 or 2 plus 3 is 5. They come out to be the same answer, but by convention, you normally see the positive first. Good answer there. Okay, next step, my friends. Fasten your seatbelts. We are taking a bigger umbrella for patterns of chemical change and calling them oxidation and reduction reactions. So double displacements, what we just practiced, are not considered redox reaction. This is a whole new ball of wax. Oxidation has a definition that says the loss of electrons. Oxidation, the loss of electrons, also will be known as the reducing agent. It forces the other to be reduced. A reduction is a gaining of electrons, also called the oxidizing agent. I'm getting us familiar with some vocabulary words that are going to be presented through our redox lesson. One of the little tricks that I use to help me remember the definition, I say, Leo the lion says grrr. Can you get that visual? Here's the grrr. Leo the lion is grrr. How might that help me remember those vocabulary words? Loss of electrons is oxidation. The gain of electrons is reduction. And now you have a visual of a lion grrring at you. Some people like this mnemonic device, oil rig. If you prefer visualizing an oil rig or a real cool lion going grrr, if I'm a Lions fan being from Detroit, we're very accustomed to losing, the Leo the lion saying grrr works for me because it's a personal connection. Oil rig, oxidation is loss, reduction is gain. That's a trick to help me remember the definitions. If you lose electrons, I'll put loss of electrons, that's better grammar. If you lose electrons or loss of electrons, you're removing negatively charged particles. You become more positive if you lose electrons. Sodium ion loses an electron, becomes +1. Magnesium ion lost 2 electrons, becomes +2. Losing electrons makes you become more positive. Correct. And if you gain electrons, you're adding negative charges in, so it becomes more negative. Going down the number line, reduction of charge, reduced. That's helping me figure out what's oxidized and what's reduced by tracking changes of charge as reactants turn to product. Alrighty. So a loss of electrons on a number line results in an increase of charge, or more positive, I'll say, up the number line. And if you're heading more negative, you know that that's being reduced. Redox reactions have a change of charge from reactants to products as electrons are transferred between reactants. Let's give an example, and the first example I have will follow a pattern called a single replacement reaction. We just did doubles. This will be a single replacement reaction where element A reacts with compound BC. Element A displaces B and forms a new product, AC. That's what we refer to as the general pattern of single replacement. And this is a picture. I've got to talk you through what's happening here. This is a piece of aluminum foil in a solution of copper 2 nitrate. The copper 2 nitrate, copper when it's in solution is that royal blue color. The element is aluminum. Notice that it's solid. It's just a piece of wadded up aluminum foil. And it's in a solution of copper 2 nitrate. And so when I write out that formula, copper is a +2, nitrate is a polyatomic ion, it's a -1. So when I crisscross, I get CuNO3 taken twice. And that is in a water solution. See the cup of water and the copper nitrate's dissolved in it? So it receives an AQ as an adjective. We have an element reacting with a compound. The pattern is a single replacement, single displacement, single exchange, whatever you want to call it. We can see as time goes by, evidence of a chemical change. That actually is a thermometer. On the left side, the digital readout is 20.5, and on the right, it's 29 degrees Celsius. So heat is being released. That's next chapter. That's thermochemistry. Heat being released, we'll learn, is called exothermic. Gets warm to your touch. Evidence of change. Heat comes out. What else do you see in that beaker? It's hard to tell because it's... So instead of the shiny silver color of aluminum, what does it look like now? Kind of brownish, reddish brown. What is that coming out of solution? Beautiful. The aluminum kicks out the copper. The new element that you see being formed is the solid copper metal. That's the reddish brown, or it looks dark, being deposited. And you can see it even falling out of solution on the bottom of the beaker. And I noticed that instead of being this nice royal blue color of copper nitrate, it turns grayish. The solution is no longer copper nitrate. The new solution is aluminum nitrate. Yep. I'm not balanced yet, but I have a good-looking skeleton. I'm going to hit the light back on us so we can see. That's my skeleton so far. I had a piece of aluminum foil in a solution of copper 2 nitrate. Time goes by, and we have a single replacement reaction occurring. Going into solution is the aluminum ion, and falling out of solution is copper metal. The two metals have exchanged places. To balance this, I notice there's 3 nitrates on the right, 2 nitrates on the left. The lowest denominator for a 3 and a 2 is a 6, so I want to turn them both into 6s. So I'll need to place a 3 on the left side for copper 2 nitrate and a 2 on the right side, and that helps me balance that polyatomic ion nitrate. There's now 6 units of nitrate on both sides. When I do so, I also need to repair the metals So when we're done balancing the molecular equation, I would read that. 2 moles of aluminum react with 3 moles of copper 2 nitrate to form 3 moles of copper metal and 2 moles of aluminum nitrate. This pattern is called a single replacement, single displacement. 2 elements exchange places. So, great question. Let me address that with the difference between an aqueous ion, ions only exist in water, is that the ions carry their charges. An element, in its elemental form, aluminum is solid. It's a piece of foil in my hand. That's not an aqueous ion. That's aluminum foil as an element. So no charge to any element in its natural form. And what you just allowed me to do was explain one of the rules for assigning oxidation numbers. We will learn, I think in a slide or two, that any element in its elemental form is assigned a 0. In nature, aluminum is a solid. Right now, there's no charge on it. Its oxidation number is 0. On the right side, copper was in solution on the left side, but it came out to form elemental carbon, the metal of carbon. Any element in its natural state is assigned a 0 for its oxidation number. Aluminum went from a 0 to a +3. On the left side, it's a 0, elemental form, and now on the right side, it's charged because it's in solution as an ion. When it becomes from 0 to +3, is that oxidation or reduction? Becoming more positive. Look in your notes, oxidation or reduction? Beautiful answer, oxidation. So when I write that, kind of connecting those two, you'll see me write that as the Leo half reaction, the oxidation half reaction. Aluminum was oxidized. Aluminum was oxidized, therefore, it's called the reducing agent. Copper went from a +2 to a 0. +2 down the number line to 0. It's actually becoming more negative. Think on the number line, if you're up here at a +2 and you move down to 0, that's negative on the number line, moving left. Therefore, it was reduced. The copper ion was reduced to elemental copper. So we would say that the copper nitrate was the oxidizing agent. The pattern of change is single replacement. I can get that pretty easy. It's the redox umbrella that we have to apply to it. And redox is this big umbrella for any kind of equation where you find things that change charge from the left to the right. Aluminum started at a 0, went to a +3. Copper started at a +2, went to a 0. They changed charge. Now I can recognize it's a redox reaction. When I write the net ionic equation, I see only one spectator. Because it's not the same to say aluminum 0 and Al +3, they are not the same thing. Copper's a +2, now it's a 0, they are not the same thing. But what did not change is the polyatomic ion nitrate. It's still swimming in the water. So when I write the net ionic equation, I have 2 aluminums reacting with 3 aqueous ions of copper, forming, you don't want organic, I'm sure, forming 3 copper metals and 2 aqueous ions of aluminum. I eliminated the spectator of nitrate. When you look at a redox reaction, they must be balanced by both mass and charge. What do I mean by that? By mass, I go, okay, 2 aluminums, good. 3 coppers, good. So I'm using my coefficients to balance the number of each type of element. But what else is true about that equation? On the left side, what's the net charge of 3 aqueous ions of a +2? +6. Over on the right side, what's the net charge of 2 aqueous ions at +3? +6. I have to have them balanced by both mass and charge for a redox reaction. When I asked you what's oxidized and what's reduced, what became more positive was oxidized. What became more negative was reduced. What is oxidized is called the reducing agent. What is reduced is called the oxidizing agent. Vocabulary practice. Take a moment, check in with a neighbor nearby, and let's describe what a redox reaction did. Talk to your neighbor. And, thank you, and charge. A question or a stretch? You put your hand up. Just stretching? Okay. Good. Friends, let's try one more, very similar but different. We're going to talk about redox reaction. I'm going to stick with a single displacement, but show a second example. And I did so with showing the equation. On the far left is a piece of copper wire. So you just take it off the spool, you snip it, and copper wire, when it's that thin, you can just kind of wrap it around your pencil and make a little spring of copper. So that's a piece of copper wire. We place into the beaker, okay, so by the way, copper, that's this guy, right? Solid copper wire. We place that copper wire in now with a solution of silver nitrate. So the gray colored solution is silver nitrate. Time goes by, and what do you start seeing deposit on the wire? Silver. You're absolutely right. The chemistry says those two metals exchange places, that the copper is more active. On our activity series, it shows us that copper can displace silver, who's less active in solution. And when it kicks out silver, the new element that forms is silver metal. As time keeps going by, more and more and more silver gets deposited out, and you start to see it look real mossy. When it first starts, it's nice and shiny and looks like silver that looks valuable until you let it go longer and longer, and it keeps growing, and it gets all mossy looking to it. It's not very pretty. What's now in solution? Can you read that? It used to be copper on the metal, but now the copper forms an aqueous ion. So in solution now, we have a copper 2 and a nitrate, and that's that blue color that you see for copper. Just like the previous slide, we started with copper in the water, so it was pretty blue. This time we're putting copper back into the water, so we see the blue solution, shows me copper. Our equation shows 1 mole of copper solid reacting with 2 moles of aqueous silver nitrate to form 2 moles of solid silver and 1 mole of copper 2 nitrate in solution. Did I balance that right? 1, 2, 2, 1. That works. 2 silvers, 2 nitrates, 1 copper, we're good. So with my pattern of change, the single replacement pattern, the 2 metals exchange places. A hand. It came from right here, that blue color due to the copper 2 ions formed. It was given, and I like your question because copper lives in the heartland of, I don't know your charge by where you live. Perfect. So in this example would be the only way I would know to put a +2 charge on it is because it's sharing with me the charge from the picture itself. And that detail was critical to be able to finish the equation. Excellent question. So as a single displacement reaction, we see the pattern of change. 2 metals switch places, 1 place out of solution while the other goes in. This is also a reaction called a redox reaction, where changes of charge occurred. We see that any element in its natural state, how we find it in nature, is assigned an oxidation state of 0. In nature, the elemental form of copper is a solid metal. It's assigned a 0. The elemental form of silver is assigned a 0. When there are ions in solution, the oxidation state is equal to its charge. The oxidation state of silver is a +1. The oxidation state of the copper in solution is a +2. We have things changing charge from the left to the right. If copper started as a 0 and went to a +2, it's becoming more positive on the number line. Therefore, that's the oxidation half reaction. To lose electrons makes it become more positive. Copper is being oxidized, therefore it's called the reducing agent. Silver went from a +1 to a 0. It's becoming more negative on the number line. There is your reduction half reaction. Silver nitrate is the oxidizing agent. Notice how I'm using the entire reactant to call an agent. So copper, since it was oxidized, it's called a reducing agent. Since silver nitrate was reduced, it's called the oxidizing agent. Yes, great question, because it's not like I can go to the shelf and pull out a reagent of just silver ion. It has to have a last name. So I can pull off the shelf an element like copper, but I can't pull off an ion. It comes as a first and a last name. So you identify the agents by the entire compound. When I describe what's oxidized, it's the silver ion that was oxidized, because nitrate is the spectator ion. When we ask you to write the net ionic equation, we eliminate the spectator, and we have solid copper reacting with 2 aqueous ions of silver, forming 2 silvers as solid and a 1 aqueous ion of copper. Notice it is balanced by both mass and charge. There's the same number of each element on both sides of the equation, and the net charge on both sides of the equation is balanced. It's balanced by mass and charge. 2 silvers, 1 copper, oh yeah. Net charge on each side is both +2. Yes. So the only choice in nature for copper is a +1 or +2, and you could balance the equation using a 1 or a 2. It would look different than this one. You'd have all 1-to-1 ratios. If it's a copper +2, you have a 1-to-2 ratio. You wouldn't know its identity just by looking at it. Copper 1 nitrate in solution is royal blue. Copper 2 solution is royal blue. So you'd have to be told. I skipped the complete ionic by recognizing nitrate as the spectator ion. I encourage you to skip writing the complete ionic equation. Go from molecular to net, and that just takes practice. Let's look at a redox reaction for a combination pattern. I've showed you 2 examples of single replacement, but remember I said it can be combos, it could be decomps, it could be singles, it can be combustions. There's a variety of equations that fall under the redox umbrella. Let's model a redox by considering the combination of elemental sodium with elemental chlorine to make table salt. Elemental form of sodium is Na, and it exists in nature as a solid metal. It's reacting with the elemental form of chlorine. In nature, how do we find chlorine? Horses need oats for clear brown eyes. It's a naturally occurring diatomic molecule. Is it solid, liquid, or gas? It's in a gaseous form. Do you know your periodic tables are color-coded for that? The red are gases. Chlorine is symbolized in red. If it's kind of dark or outlined like this is gray, those are solids. And the only 2 liquids are bromine and mercury, right? Just so we know how to find what state of matter they're in. Natural state of chlorine is diatomic Cl2. It's in the gaseous form. It forms a salt called sodium chloride. Sodium is a +1 when it forms a charge. Chloride is a -1 when it forms a charge. Sodium chloride, electrically balanced, would be NaCl. And there's no water here, so sodium chloride would be a salt as solid. That's a beautiful skeleton. It's not yet balanced. I'll balance the chlorines, NaCl, and then I have to back the bus up and fix the sodiums, right? So 2, 1, 2. That's called a combination pattern. It's a building product, right? 2 smaller things combined to make a single product, combination. But it's also classified as a redox reaction. This reaction has things that changed charge from the left to the right. Any element in its natural state is assigned a 0. Sodium and chlorine are 2 elements in their natural state, so both things on the left are 0. Sodium went from a 0 to a +1. Chlorine went from a 0 to a -1. Those things changed charge. If one of them's oxidized, the other must be reduced. There's a transfer of electrons. So the Leo half reaction is the one that becomes more positive, and the reduction half reaction becomes more negative. The sodium, since it was oxidized, is called the reducing agent. Since chlorine was reduced, it's referred to as the oxidizing agent. How many electrons have been transferred? I'm hearing two answers, 1 or 2. When sodium, 2 NAs, formed 2 Na plus, 2 units of Na plus is a loss of 2 electrons. Cl2 went to 2 Cl negative. That's a gain of 2 electrons. So each half reaction has to also be electrically balanced. Correct. To gain the electrons, you add them in to the reactant side. To lose electrons, you show that on the product side. The number of electrons lost must equal the electrons gained, so when you add the two half reactions back, they would just cancel each other out. We practiced 2 single replacements and showed you also that they're redox. Here's a combination, but it's also a redox. There are so many examples of redox that fall under those categories that we've been practicing. Let's take some time to formally state each one of these rules of how to assign oxidation numbers. I need us to master those rules, because I'll never stand a chance of finding what's oxidized or what's reduced unless I know how to assign oxidation numbers. Rule number 1, we've used it a few times. Rule number 1 reads, the oxidation number of any atom in its elemental form is always 0. The way I find it in nature, sodium metal, 0, chlorine gas, 0, from our previous example. Any atom in its elemental form is 0. Rule 2, we've used a few times. It says the oxidation number of a monatomic ion is equal to its charge. Monatomic ion, Na plus, its oxidation number was +1. Cl negative, its oxidation number was -1. Monatomic means one atom carrying a charge. When I look at that example, sodium chloride from the previous slide, sodium as an ion is +1. Sodium as a metal was assigned a 0. Chlorine as a diatomic gas was assigned a 0. Those are its elemental forms. But if they're hooked together in a compound, we now call them charged ions. The oxidation number is the same number as the charge it carries. Rule 2. Rule 3. It's the oxygen rule. It says oxygen is always, 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 always a -2. Oxygen, right here on our chart, we learned is a -2. Except for the one little time in nature, instead of being an oxide, it's listed as a peroxide. A peroxide is a different ion than oxide is. How can I recognize a peroxide? I know perhaps you've heard of the word peroxide. Hydrogen peroxide might be in your medicine cabinet at home. You get an owie and you put it on and it bubbles and cleans out germs. Hydrogen peroxide. You get your ears pierced and you put some peroxide through to keep it clean as it heals. The bubbling is from the oxygen gas that's released from peroxide. Let's compare these two formulas to make an understanding of the peroxide rule. In nature, there's a compound called water, H2O. In nature, there's a compound called hydrogen peroxide, H2O2. What do you notice about the formula between water and peroxide? When you see the O2, written after a first family metal or hydrogen, it looks odd to you, doesn't it? H2O2 looks like an odd formula when I know it should naturally be a +1 -2 for hydrogen and oxygen. When you notice that odd configuration, and it doesn't happen but a fraction of the time, 99% of the time, oxygen's always a -2, unless you see a peroxide, and now it becomes a -1 overall. We'll practice the oxygen rule. I remember it. Oxygen's a -2 unless it looks weird. Rule 4. Hydrogen is always a +1 when it's combined with a non-metal. When it's combined with a metal, it now is a -1. Let's give an example of this to help make sense. Here's hydrogen combined with a non-metal in a water molecule. What is the oxidation number of hydrogen when it's attached to a non-metal? It's always a +1. Hydrogen lives over here. It's a +1. What if you see it hooked to a metal? Therefore, it would be written last. Sodium hydride, lithium hydride. You have the ending changed to "ide." "Ide" means that it's now a negative ion. Sodium would be a +1, hydrogen's a -1. When it hooks to a metal, you'll see it written as the negative position. In most periodic tables, well, I won't say most, some periodic tables place hydrogen not only on top of lithium, but you'll also see it on top of fluoride, because it can do either one. It can accept or lose an electron. Rule 5, I like this one. There's no exceptions to it. It just tells me fluoride, never a choice. If you see fluoride, it's always a -1 charge. Fluorine right here, -1. That's good to know. If you see a fluorine, assign it right away. And it says, I know this from writing equation, it says by the time I'm done adding all the oxidation numbers for a compound, the total charge has to be 0. It's got to be electrically neutral to be a compound. And if it's a polyatomic ion, it's got to equal the charge. So when we start practicing what's oxidized, what's reduced, these 7 rules or guidelines help me assign oxidation numbers. And once I can assign an oxidation number, I can detect what's changed from the left to the right side. Let's practice, and I pulled some sapling questions. I'm going to practice these 7 rules. And I don't care if you memorize the 7 rules, the more you use them, the more natural they'll become. Here is a problem from sapling. It says, let's assign the oxidation state of each element found in potassium dichromate. That formula is K2Cr2O7. Let's focus on that one first. Potassium dichromate. I'm going to write that larger so I can just kind of work through and kind of process with you. First, a piece of advice, do the first one, do the last one, and leave the middle element to balance charge. Alrighty? So I leave the chromium for last. I know the first position, I know the last position, leave the middle one for last. Alright? There's an oxygen rule. Rule number something was about oxygen. It said oxygen is always a -2, unless it's a peroxide, but this isn't part of a polyatomic ion. So I know with confidence the oxidation number of oxygen is a -2. The total contribution of charge, 7 units of a -2, is -14. I know from the last rule that says by the time I'm done assigning oxidation numbers, all the positives and negatives are going to add together to give me 0. If oxygen is assigned a -2 and there's 7 of them there, the total charge so far just from oxygen is at a -14. Who else do we know? When I find potassium on our periodic table, it's a monatomic ion. It's an ion written in the first position. I know it's positive. By looking up its charge, the oxidation number is a +1 charge. There's 2 of them there, so the total contribution of charge from potassium is at a +2. Then I leave the middle guy to create an electrically balanced compound. I've got a +2 and a -14. They have to give me 0 by the time I'm done adding them all together. What goes in the box to give me 0 by the time I'm done summing the values? It's a +12. You're giving me both answers, right? It's a +12. There's 2 of them there, however, so I was getting the total answer of +6. To balance the charge, both chromiums had to give me 12 altogether, so each one is contributing a +6. We've just assigned the oxidation numbers of each element in potassium dichromate. This is sulfate polyatomic ion, SO4 -2. We're being asked to write down the oxidation numbers for each of the elements. Instead of being a neutral compound, it's a polyatomic ion. So instead of adding to be 0 by the time I'm done, it has to equal the charge of the polyatomic ion, -2. I know oxygen is always usually a -2. There's 8 of them by the time I'm done, a total contribution of a -8 from 4 oxygens. Oxygen is a -2. Its contribution when there's 4 of them is at a -8. What do I add to a -8 to land at -2? A +6. The oxidation number of sulfur is +6. Again, establishing these rules helps me identify the change of charge from oxidation and reduction. There's a series of these on your homework. Here's a compound, COH2. There's a rule that says oxygen is always, usually, a -2. So I know right off the bat what to assign that oxygen. There's a rule about hydrogen. Hydrogen, when bonded to non-metals, and that's what C's and O's are, they're non-metals, are always +1. Hydrogen is a +1 when bonded to non-metals. Oxygen is a -2. Right now, the total contribution of charge gives me 0. What added in that would keep me at 0? What is the oxidation number for carbon in this compound? It is 0. This takes practice, doesn't it? Here's FeBr3. That's called a binary ionic compound. This goes by rule number 2. It just says monatomic ions have oxidation numbers equal to their charge. Uncrisscross is another way of saying that, and find the charge on each of those monatomic ions. You know bromide by where it lives. Here's Br on the periodic table. When I find its charge, it's a -1. There's 3 of them there for a net of -3. Iron lives in the heartland of the periodic table that I don't know its charge by looking, but I can deduce its charge by creating an electrically balanced compound. So the iron is a +3 and the bromide is a -1. Both are monatomic ions. Rule 2 says they're going to be equal to its charge. How about on your paper to turn in? Try this one. Manganese 3 perchlorate. Manganese 3 perchlorate. What is the 3 outside that parenthesis of the polyatomic ion? What does that tell you about the charge for manganese? It's a +3. That's why it's there. If you uncrisscross, you knew the manganese had to be a +3. On the polyatomic ion chart, you find a perchlorate. ClO4 is perchlorate. It's in the first column, maybe a good ways down toward the bottom on the first column, and you see that its charge is a -1 overall, perchlorate, ClO4 -1. So when you crisscrossed, that 3 told you the charge on permanganate. This 1, that's not there but we know it's there, told us the charge on the perchlorate as -1. We crisscrossed to write those charges. So uncrisscrossing showed us that the manganese had to be a +3. Then we have this polyatomic ion buried in a parenthesis with a 3 outside. I think a good strategy, I think it's easy, you might find it as well. Why don't we take it out of the parenthesis and just make it equal to the -1 charge of perchlorate? Then I don't have to worry about the parenthesis and distributing through. Pull it out, make it its polyatomic charge of -1. There's a rule about oxygen. The rule says it's always, always, always a -2, giving me a net negative of -8 altogether. The polyatomic is -1, so what will chlorine need to contribute to keep it at a -1? What is the oxidation state of chlorine? You're staring though. +3 for the manganese, +7 on the chlorine, and a -2 for the oxygen. Let's bring that to the next step of applying it. So we practice getting those charges. What do we use them for? I like that strategy because if I left it, and here's another strategy, and you might like this one just as well. You could write this and distribute the 3 through it. And once you knew this was a +3, this was a -2. You know, that's another strategy. 2 times this would be -24. That's a +3. So this would have to be a +21. 21 divided by 3 is 7. You could get there that way, or unbury it from the parenthesis and set it equal to its charge. Either one will get you the same place. I think this is a smidgen easier, but just depends on how you want to approach it. Great question. Here's one from your homework that asks you to recognize assigning oxidation numbers and then actually using them to find what was oxidized and what was reduced. This can go on just paper for you. You'll want that when you get to your homework. I have reactants, products, which one's oxidized, which one's reduced. I'm going to write them bigger so you can see them. Here's ClO4 forming KCl and 2 oxygens. Any element in a monotonic form, the charge is equal to the ion's charge, so K is a +1. Oxygen in a compound is always usually a -2. So if potassium's contributing a +1, oxygen is a -2 for a total of -8. The chlorine here is assigned a +7. On the product side, chlorine is now in a binary compound. It's just took to potassium as a +1, so now its charge must be -1 to make the electrically neutral compound. On the product side, oxygen is written as a diatomic molecule. Oxygen is written in its elemental form. Any element in its elemental form is assigned a 0. Potassium didn't do anything. It's a +1 and it's a +1. The chlorine went from a +7 to a -1. A +7 to a -1 is a reduction of charge. It's becoming more negative. Oxygen went from a -2 to a 0. -2 is moving up on the number line to land at 0. It's becoming more positive, therefore it is oxidized. We said potassium did not change charge. It would be considered a spectator ion. Chlorine went from a +7 to a -1. That's reducing the charge on the number line. The element that's being reduced was chlorine. Oxygen went from a -2 to a 0. That's increasing on the number line. Therefore, oxygen was oxidized. In this pattern of chemical change, we had a single reactant breaking into simpler pieces. What's the general pattern of change where you see a single reactant breaking into simpler pieces? Beautiful. It's called a decomposition, breaking it back into smaller pieces. Decompositions are also called oxidation and reduction reactions. Trying to do as many homeworks as I can. Notice here, this is a net ionic equation from a single replacement reaction. I have an elemental form of iron plus an aqueous ion of copper, forming an aqueous ion of iron, that's fun to say, aqueous ion of iron with copper solid. Iron started as a 0 and went to a +2. Copper started as a +2 and went to 0. There is a change of charge, therefore we know it's called an oxidation reduction reaction. When copper went from +2 to 0, it's decreasing on the number line, therefore it's said to be reduced. When iron went from 0 to a +2, it's getting more positive. Therefore, we know that it's oxidized. The substance that gets oxidized. Now, notice that you have ions and charges. You want to be sure you're only selecting from the left side of the equation. The reactants. That's what's oxidized. That's what reduced. Don't pick something from the product side. You want to pick to answer from the left side. So what was oxidized was the iron metal. Right off the bat, now that I know it's oxidized, the vocabulary word that's assigned to it is called the reducing agent. When copper ion went from a +2 to a 0, it was reduced. Therefore, it is the oxidizing agent. Do not select from the product side, only select from the left side, the reactant side, for oxidation and reduction agents. Copper over here, copper ion, alrighty, because the ion is on the left. You try one to turn in, the last one you'll do for me today. Turn this one in. Magnesium solid with chlorine gas makes an aqueous ion of magnesium and 2 aqueous ions of chloride. There must be water on the arrow. I don't see water there. How did that happen? This equation makes me kind of chuckle from its sapling. How would a gas and a solid combine to make water solution? It's like magic. So just so that doesn't bother you like I know it is me, I'll put water on the arrow to say we're dissolving it. Any element in its natural state is assigned a 0. Any ion is assigned its charge. Made a tickle. Right off the bat, you know not to choose the ions. Those are off the table, right? Because they're on the product side. We have to decide if it's elemental magnesium that's oxidized, or is it chlorine that's oxidized? And you'll have the other answer then. When you have yours done and ready to turn in, I'd like you to pick up one of these sheets. When you turn your attendance sheet in, pick up one of these sheets. It's got a front and a back. I'd like you to look at this over the weekend and bring it back completed Tuesday. I won't grade it right or wrong. It's practice for what we've been working on. We'll probably start with a compare and repair, but I want you to practice over the weekend. So pick this up and bring it back Tuesday with you completed. When you have this finished, that's your ticket out the door. Pick up your assignment sheet on the table. Nope.